Okay. Okay, so any question up to this point of time? No? Hey.
Professor, I'd like to know, for example, after we group our data set up by the dendrogram, how can we pull out or extract the information of those groups and apply it to our data set table?
Now, that's why we are using this line of code, right? You don't really need to plot the dendrogram, okay? After you do this line of code, you already have a hierarchical clustering object, okay? And you can you use this function to cut this object into the number of group that you can specify. Okay? So, and then you can actually put the result of this cut tree as a column in the original data frame, right? So the grouping vector will be here. Okay? Will be W $group, right? Will be within this column. So if you do a table of this column, you can see the group size of each of the 8 groups. Does that answer your question?
Because I tried to print the W group out, and all I see is the number from 1 to 4. For example, I would like to know, like, the group 1, I want to know the total number of products they bought. And how can I know?
You can look into this data, isn't it? Now the data has the group number, right? So the first data point belongs to group 1, the second belongs to the group second, right? And this data point will belong to group 5, right?
So we can reuse this data to draw another type of plots.
Right, that's what we are doing now. That's what we are doing. Okay, so as you can see that now we can use this group as color, right? See that? So because for practice reason, right now we are only using 2 grouping variable, right? So I can very easily plot them in use these 2 variable as the x and y axis, and then I use group as the color. I draw the point, right? See, this is the result. I can see it better here. That is the result, right? So every group of this data point, they are clustered. They kind of like are clustering in about the same space, right? Within this 2-dimensional space, right? And as I told you that in this 2-dimensional space, the distance imply difference, right? So because they are close to each other, it means that they have similar buying behavior, right? And is that what you are asking for? Right? That's that. So very simply, you just like use this grouping variable as a color. Okay. Now let's practice. Let's clustering with 5 variable, right? This time. Now the difference is like, see, is 3, 4, 5, 6, 7, right? 5 variable. And the rest of the pipe is the same, right? So whenever you want to do hierarchical clustering, you actually just copy and paste this line and replace here with your own data, right? And make sure that you specify the grouping variable that you want to use, right? And then you will obtain one of these clustering object, okay? You can plot the object, but usually this is not necessary, right? What you really want to do is this, right? You cut the clustering object into K group, okay? Okay. And usually you will like transfer them into a vector. Otherwise, it would be an integer, right? Okay. But that 1, 2, 3, 4, 5, 6 is not integer, right? Because they are group numbers, so actually they are kind of like categorical things, right? So for easier for better display, you better like transfer them into vector, and then put them as a column in your data frame. Okay, so let's forget this. This is just to draw a dendrogram with a beta look, but you don't really have too many practical usage, right? Just to plot the beta dendrogram, right? Okay. Now, but as I told you, right? If you want to if you have do a clustering in a high dimensional space, right? It's very difficult to plot, right? Okay. Usually you have to like compress the high dimension into a lower dimensional space before you can do the plotting, okay? And this dimensional reduction is actually very easy to do, okay? This is the data, right? And this data contains like 6-dimensional data. See that? 3, 4, 5, 6, 7, 8, right? So this is 6-dimensional data. And when you want to do a dimensional reduction, you simply call this function called PCA, right? Again, there are many different dimensional reduction methods. And the one that we use the most in data analytics is called PCA, right? Okay. And then what? How is it? This is so strange. Okay, and then after you do the PCA, we do a visualization. Okay, you can do the visualization. So, but actually this default visualization is not very good. Okay, usually you need to do some as you are using ggplot, right? You need to specify a few things before you can have a beta plot. Okay, let me explain the syntax a little bit. Okay, so this is the way to like make this final plot. Okay, the clustering with dimension reduction. Okay, let me go to here so it's easier to explain. Now you first of all we need to do this. So as you can see that if I simply do this, if I simply call this PCA, right? Okay, and Let me do it from the beginning. I simply code PCA. Let's see what will happen, okay? If you simply code PCA, it actually will tell you, it will give you something like this, okay? It actually would like, this data is like a 6-dimensional space, right? And it kind of like compresses the data into a 2-dimensional space, okay? It do the compression, and then in the first plot, it will draw the data point, okay? 440 point, right? So after the compression, after it compresses from 6 dimension to 2 dimension, this is the data. And then it will give you another chart to show you the original dimensions. This is the original dimension, right? Originally, you have 6 dimensions, isn't it? Right? Milk, grocery, detergent, daily, fresh, frozen, right? Originally, you have 6 dimensions. And when you compress this 6 dimension into 2 dimension, every original dimension will have a direction, right? You don't have a direction in this reduced space, isn't it? Right? So the default plotting of this PCA is to generate these 2 plots. It will generate one. It will generate one data point, right? And then it will generate one plot for dimension, okay? But usually we want to usually we want to see it this way, right? There's another function called byplot, which means I want to plot the data point at the dimension in the same plot, okay? So other than plot the point and the dimension separately, if we plot them separately, we cannot do observation, right? So we want to like plot them together, right? So if you want to plot them together, so you say, I don't want the PCA to do the graph. I supplace the plot of PCA, and I plot this PCA by plot instead, okay? Now, as you can see that the data point and the dimension, they are plotted in the same space, in the same plot, right? But it's still very ugly, right? Okay, so so we need to do some like, for the rest of the code is just to like do some, make it look better, right? Make the graph look better. So the first thing is we want to specify, for the detail you can go to the online help for this function. In the online help of this function, you will see all of this argument, the meaning of this argument, okay? The first argument I use is that I specify the color of every individual. Every point, let me do it here, it's easier, I think. Now here, color point individual, it means that I want to specify that every point is a retailer, right? Okay? So every data point, I want to use the group as the color. IND means the data point. The color of data point, I want to use, I specify the color of every point by the group number, right? Okay. So in this way that it will be divided into groups. And then I'll see label called variable. It means that I don't want to label each data point. I want to label the variables. See that? Okay. The default is both. So when they will have a label on every data point, it will be like too messy, right? Okay, so in this case, I only want to label the variables. And then the point size and point shape. See that? This is the point shape. Okay, point shape is 19. And mean point, it means that by default, it will have a central point also draw here. Okay, and it's kind of confusing, right? So usually I will like disable the mean point. The mean point is actually the group mean. Okay, so I disable group mean. And this add ellipse and ellipse label, actually these three parameter is trying to add a convex box at the boundary of each group. Okay? If you do not use these three things, you will not have this group boundary. Okay? So these three arguments is just to add a boundary on the group. Okay? And palette is just to choose the color palette. Okay? And repel equal to true is sometimes the label would overlay with each other, right? So I just repel the label so that they don't overlay with each other. Okay, so well, there are more graphical detail variable that you can use, but usually you just like copy and paste this set of variable and do some modification, will have a very nice result. See that? Okay, so we have spent about an hour and a half trying to explain what is clustering, what is dimension reduction, and we demonstrate how we can do that in an R environment. Okay, as you can see that in R, to do clustering is so easy, right? You start with the data, right? And then you always use this pipeline to generate a hierarchical clustering object. And then you cut the object into the number of groups that you prefer, right? Put the grouping, put the clustering vector as one of the column in the data frame, right? And then you can do the visualization, okay? But if you do it this way, you will not see the original dimension, right? So usually you want to usually you will have a lot of variable to cluster, okay? And usually you would like to plot the grouping result, the clustering result with this reduced dimension, okay? And this is the outcome. And doing dimension reduction is actually even easier, right? As I told you, that you just put the data into a PCA function, and for better visualization, it basically turn off the default graph of PCA and put the result to a biplot, okay? So it would plot the data point and the dimension in the same plot, okay? And would do some argument to make the graph better looking, yeah. And that is the way to do clustering and dimension reduction. Any question up to this point of time? No? No question? Okay, so let's move on. Okay, I'll try to give you some more practical real business application of clustering and dimension reduction, okay, in the following two notebook. Let me do some cleanup, okay. Now let's take a look at 7b, okay. Now, 7B is actually an airline customer segmentation. Okay, it's airline customer segmentation. So we load the data, and as you can see that the what it looks like there's some problem. Let me try again. Sometimes my R Studio will have some interference problems. This what? Okay, it's okay now. I don't know why, but still I cannot see the. Yeah, I can see the data. Now, this is the original data. So we have 4,000 members. Okay, airline actually have some loyalty program, right? You can like collect the point, and sometimes you can like use the point to use the mileage, right? To you can accumulate mileage, and you can use the mileage to like exchange for some ticket or some upgrade, something like that, right? Okay, so this is kind of like the airline the loyalty program data. Okay, so every record represent a member. Okay, and this is the explanation of the columns. The first column is the balance, right? The my regular mileage remains, and qualified miles, the high class mileage remains. I really don't know what it means by high quality mileage. Maybe they like if they fly a business class, they will have like high quality mileage, something like that. Okay. And this is the balance, right? It's also the balance. Okay. So, and then this field. Let me explain this two column first. This is the mileage obtained by flight in the past 12 months. Okay? The mileage obtained by flight in the past 12 months. Okay? And this is the number of flight in the past 12 months. Okay? So if this is a 5, it means that this member like fly in this airline 5 times. Okay? And if this like 55 thousand, then it means that this customer in the past 12 months it fly in this airline 55K miles. Okay, so this is the number of time it fly in 12 months, and this one is the mileage. Okay, and sometimes when you are using this mileage accumulation program, it sometimes will get the point by not by flying, but by like car rental. By if you live in a hotel that has alliance with the airline, you will actually earn some point, earn some mileage, isn't it? Right? So again, this is for the past 12 months. The past 12 months. Okay? And this one is the number of transactions, the bonus mileage, not by flying, non-flying transaction, the number of non-flying transaction. Okay? And this one is the mileage obtained by non-flying transactions. This is the number of time, number of transaction, and this one is the mileage. Okay? Similar to like this one is the number of fly, and this one is the mileage obtained. Okay? And all these four columns is for the past 12 months. Okay? And this is the day since enroll. The day since enroll. So this is kind of like seniority. Get it? Okay? So this is the data. This is the airline, the CRM data, you can say that. Okay. Now, the first thing is we want to do standardization. If you look into the scale, right, then you can see that from here you can see that the necessity of standardization. Okay. You can see that for the number of transactions, the scale is from 0 to 86, right? But for the scale of balance, it's from 0 to 1.7 million. Isn't it? Right? So if you do not do scaling and try to like do dimension reduction or clustering, right? The weighting of this scale would overweight everything, every other column, right? Isn't it? Right? So before we cannot use this original scale to do grouping or to do dimension reduction. Before doing that, the first step is to do scaling, right? Okay. As you can see that now I call the scale function to do the standardization automatically for me. Okay. So and I put the result to the AN data frame. Okay. See? Okay. So this AN and A, they are different, right? The A is the original data. The AN is the A standardized A data, and in the standardized A data, as you can see that, if I take the mean, as you can see that, almost every the column, the average of every column becomes 0. Okay, and the standard deviation of every column is actually 1. You can see that, right? That is the effect of standardization. Otherwise, as you can see here, that the means are very different one with each other, right? Okay, the scale are some scale is less than 100, and some scale is more than 1 million, right? So we don't want that. If we want to do clustering, we have to standardize the scale. Okay. Now we do the second step of hierarchical clustering is to do distance matrix, right? So in order to do distance matrix, you usually do distance and then AN. Okay. This you need to use the scaled data to do the distance, right? Otherwise, the distance would like be dominated by the very large scale, right? The smaller scale would kind of like ignore totally, isn't it? Right? So you use this normalized data to do the distance matrix, and usually we'll use the Euclidean distance will be good enough. Right? Actually, this is a default, so you don't have to write this. Okay. And then after distance, you do the hierarchical clustering, right? Okay. Okay. And again, you obtain a hierarchical clustering object. Okay, you can plot the object. Well, plotting the object would look very, very ugly because now you have 4,000 data points, right? So usually we will skip this step, right? Okay. And we simply do cut tree, right? I cut this hierarchical clustering object into 5 groups and put the result in a vector called kg, right? Okay. So now kg is the vector of length 4,000, right? The length will be the same as like the original data, right? You actually can put the kg in the data frame, or you can keep it as a vector, up to you, right? It's just up to you. Okay. Now I can examine the group size, right? Okay, so up to this point, what have we do? We actually, this is the original data, right? Original data have like 1, 2, 3, 4. You have 7 numeric variable, right? And using these 7 numeric variable, first of all, we kind of like standardized, right? This numerical data, right? So they have the same scale, okay? So they have the same scale. So in the reason that we want to have the same scale is when we map it into a space, okay? Every dimension have the same weight, right? Okay. And then we using the standardized data to calculate the distance, use the distance to do hierarchical clustering, right? And then we get the result of the clustering by this function, okay? And then, actually they are, as I told you, there are many different ways to do clustering. Another way to do clustering is called k-mean. Let me, actually you can just put in the data and then say 5, okay, and then okay. The k-mean is actually an easier way to do clustering, okay. It will also generate the clustering vector, okay. So you don't, as I say, there are many different ways to do clustering. Hierarchical clustering is one of it, okay? And sometimes when your data points are, but hierarchical clustering has a limitation, right? Because you want to calculate the distance matrix so that the number of data point has the limitation. Usually when you have a data point more than 10,000, you cannot use hierarchical clustering, right? You will need to do the k-mean clustering, okay? And k-mean clustering is a lot easier because it basically you will do scaling automatically for you, okay? And then you don't need to calculate the distance metric. It will do it for you automatically, right? All you need to do is to call the k-mean function and give it the data frame, okay? And then tell him how many groups you want to cut, right? And then use this syntax to extract the cluster information, right? So calling k-mean is like actually a lot easier than using hierarchical clustering, okay? So you can, if you're doing hierarchical clustering, you are doing something actually like a scale. You need to do, after scale, what you need to do distance, right? Okay. Okay? So this is the way to do hierarchical clustering. And then you need to cut tree, right? Okay. This is the way to do hierarchical clustering. Okay? And this is the way to do k-mean clustering. Okay? Well, now you might have a question, which algorithm is better? Well, there's no objective way to determine to compare the clustering method, right? The clustering is like you try and error, right? And there is no it really depends on the result. The fitness of a clustering, it really depends on how the results fit your purpose. Okay, so usually you can try hierarchical clustering. You can also try k-mean clustering. It's up to you. Okay, and now we are using hierarchical clustering. Now, after you do the clustering, you want to examine the group characteristic, right? And the first thing you want to do is to see the group size, and then you can actually see the if you want to examine the characteristic of each of this group, the best way is to do the mean, right? This split is actually splitting the original data frame by this clustering vector. Okay, it split the one data frame into 5 groups. So it split this one data frame into 5 data frame, and then for each of this data frame, I do the column means. Okay, so in this way, I can see that the first group, this is the average characteristic of the first group, average characteristic of the second group, right? So you can see that this is for the original scale, okay? So you can see that if we compare the seniority, you can see that group 4 is the seniority of group 4 is the smallest, okay? The most senior group is the group 1, right? And if I want to see the balance remaining, the larger the group the balance remaining is this one, right? And if I want to compare the quality mileage, and this one is the largest one. See that? Okay? So after you do the grouping, usually the first thing to do is to examine the group size. Okay? The second thing you want to do is to compare the group characteristic. And in order to compare the group characteristics, usually the first thing is to compare the average of every variable, right? This is the variable. So you compare this variable, then you can see the characteristic of the groups. Okay. Now Now let's compare this function, this line of code with this line of code. In this line of code, I'm replacing A with AN, okay? So I'm replacing this is the original scale, right? And if I do it in the standardized scale, it's very difficult to see, to do the comparison, isn't it? Right? Okay. So standardized data is not easy to compare numerically. However, we can plot this data, we can visualize this data in this graph. Okay? Let me go here. Sorry. As you can see that the group mean of standardized data is very difficult to observe. However, we can visualize this data in a bar plot. Okay, if I put this data into a bar plot, I will actually see this. Because they are all standardized, okay? So 0 is actually the average, right? And actually, this is group 1, this is group 2, group 3, group 4, group 5, okay? And every color represents a variable, okay? So, and as I told you, that because they are scaled, so 0 is the average, okay? So you can see that the group 1 is below average for every variable except seniority, okay? So this group of member, they are low in everything, but they are very senior, right? So this must be the senior member who did not fly for some times, isn't it? Right? Okay. So see it this way, right? If I want to plot this number, the original scale number, in the same plot, it's impossible to do that because they are in a different scale, right? So I cannot do compare. Okay. However, if I do a plotting with this standardized scale, okay, I can very easily see that the characteristic, I can compare the characteristic of each of this group very easily, right? Isn't it? Okay. So now you can observe that like for this group, right? The two things that they are above average are bonus mileage and bonus transaction. Okay? Everything is low, right? They are actually new members, right? Because their seniority is actually like very low, isn't it? Right? So these are very new, this group of members are very new to us. And they earn their point basically from bonus, right? They do not fly with us, right? This new member basically kind of like enrolled from our alliance, right? They join the club by like car rental or by hotel, but they do not fly from us very often, isn't it? Right? So after reading into this characteristic, you can see the characteristics, you can see the distinct characteristic of each of the group. Okay? Now, if the result of clustering can help you to like, it's easy to distinguish, it's easy to communicate, it's easy to operate, right? For example, can you give a name, right, to each of this, right, to each of this group, okay? And can you design a marketing campaign for this group? Okay. For example, for this group, they are very senior member, but they do not fly for a long time, isn't it? Right. So I might want to have some uh, I might want to have a marketing campaign try to wake up these sleeping customers, isn't it? Right. So and for this group, they are like they basically join the club not by flying, but by hotel or by car rental, right? Which means that if we give them some incentive, right, we might be able to like acquire them, right, to fly in our airline, isn't it? Right? So take a look at this. Then, so they are easy to communicate, easy to distinguish, and they are easy to operate. Then this is a good clustering already. Okay, right? So now let's take a break, and we'll be back in 10 after 11. Okay. Meanwhile, you can take a look at this group, okay? Then for this group, and this group, okay? Can you like come up with some marketing strategy, right? Try to describe their characteristic and design a marketing strategy, and we'll discuss this after the break, okay?